now, well, I will just give you the word for your presentation, Rossella, and yeah, please enjoy the show.
Thank you very much for the introduction. So yeah, I actually work at the Data Science Institute and in the Leonardo Center for Sustainable Business at Imperial College London, half, let's say. And so the problem we work on involve a lot of different sources of data. So when in the next observe data, but also data provided by computational fluidodynamic softwares, for example, for forecasting, like for weather, air pollution, or even medical issues forecasting. And also data from, for example, Twitter, Facebook, and social media data. So I will show you something about some models that can involve any kind of data in this range. So yeah, as William was saying, the application we work on are very like we work and machine learning or data assimilation with machine learning, which is the topic we are talking about today, to lots of different applications, and together with other institutions in UK and worldwide. I'm mentioning here just the one in the UK in our project. So the main questions we try to answer in this working group where we work on data assimilation with machine learning are essentially four. So we try to improve the estimations and or the predictions. We try to speed up the forecasting in order to have like real-time predictions. We try to achieve both the improvement of accuracy and the speed up. And for that, we use machine learning with data assimilation. I will show you how. And then obviously, as we work on real-world applications, one of the main topics for us is facing big data problems, introducing domain decomposition. So just to give you a brief introduction about why we do that. So when we have any kind of forecasting model, it could be, let's say, a dynamic system. So this MP can be any kind of dynamic system. As you have seen, the application can be very general. So MP is just a forecasting system, and it can be either a system of partial differential equations or a machine learning model. Doesn't really matter. It's a, let's say, assume that MP for us is a black box. So it's a forecasting model. We are data scientists, and we have to do something to improve this forecasting model. The main problem we have is that this model is affected by several errors, obviously. Starting from simplification errors, because we are modeling some real world scenarios with mathematical equations. Then after we model the application, so the real world scenario with mathematical equation, then we have to solve that on a computer. So we have to discretize that. We have to write the algorithm. Then we have discretization of the model. And finally, when we implement the algorithm on a machine, we have to use the finite precision computations, because our machines are not infinite precision computations. So all this simplification introduce several kinds of errors. Independent from which kind of model you are applying, PDE, machine learning, even data assimilation, doesn't really matter. In any kind of model introduce this kind of errors that we can call like model errors, discretization errors, and round-off errors. All these errors are then errors on the data that we will use in our models. So it has been proved, thanks to something called backward error analysis, that any error on the solution is, let's say, proportional in some way. This is a simplification, but we can say that is proportional to some parameters, which essentially depends on 2 points. One is how you implement the model, so which kind of discretization and which kind of algorithm you implement. And the second point is the condition number of the problem. The condition number is a parameter that provides you how the error amplifies in your system. So assuming that our model, as I've said at the beginning, is fixed, so it is a black box almost for us, then these condition number and these parameters that depends on the algorithm is like they are like fixed for us. This means that the error on our solution, so the error on our forecast, the accuracy of our forecast depends on this parameter. In order to reduce the error on the forecast, the only thing that we can do is reducing the error on the initial data. Because reducing the error on the initial data, so reducing this delta, we will have a reduction of the error in the solution. This is the reason why what we try to do is reducing this delta. And we do that doing data assimilation, even with machine learning. Over the past days, you have seen data assimilation, you have studied data assimilation formally, etc. So I will not say too much about that. The only point is that that I want to raise here is that if you try to Google data assimilation, you will find that groups worldwide, depending on the application, they call that in a different way. So somebody can call it just an ill-post inverse problem. I'm a mathematician, so for me it is an inverse ill-post problem. It is definitely a computational intensive problem, an uncertainty quantification problem, because you try to minimize the uncertainty. But independent by which kind of definition you want to give to data assimilation, the point is that if you try to give a mathematical definition of the model, it is, let's say, it works for any kind of a definition. So essentially, what is data assimilation? Just to give you a quick recap. When you have, let's say, your data, then you have your model, then you have your forecast as expected, like in the previous slide. Then imagine you have any other kind of information. So obviously for weather forecast, it can be like observed data from satellites or from other kind of information. But in other application, you can just assume that you have other sources of information. Doesn't really matter which sources. Other sources that somehow you can combine together and give that to this data assimilation, which provides you a new initial condition in its basic use. That then you can give to your forecasting model to produce a more accurate forecast. I will give you several examples about that. One question that usually students ask is why we don't just use observations? Because obviously in the Data Science Institute, most of the students coming from computing, they work on data, machine learning, they don't really mind about the numerical forecasting, etc. They say, okay, but why we have to use also information from the model? We have like, why we cannot just use the observations? So the point is that if you just try to use the observations, even if we are in the era of the data, so we have millions of observations, the observations are never dense enough, and the mathematical problem that you have to solve is ill-posed. So this is the reason why, to avoid this problem of solving an ill-posed problem, we merge together the two sources of information, the model and the observation. So just I will go quickly on this because I'm sure you have done a lot of these, you have seen a lot of this equation over the past days. But just to give you briefly, for the notation in this presentation, M will be our forecasting model. H is our observation mapping, the observation operator. And then G is the, let's say, it's just a diagonal operator when you have a 4D model. In any case, when you want to solve a data assimilation problem, essentially, you try to minimize this cost function. I will show you then most of the common data assimilation models can be derived from this cost function. So this cost function, where in G there is the model and the observation operator, and U is your unknown, so the variable that you are going to minimize to have your data assimilation result. B is your observation, U0 is your initial condition, your data from the forecast. So obviously, this is in a time window. So you have like the time window, you have several observations, and then you have one initial condition. This is the 4D approach. I'm sure you have seen this, but in case you have a fixed time, then this is simplified in this. Why I'm saying this is just to say that from that formulation, that function is called Tikhonov regularization function. You can derive, depending if you try to solve the problem as with a variational approach or with solving the normal equations, then you will have the variational data assimilation or the Kalman filters approach. Then there are the ensemble Kalman filters and others, but these are more of the popular approaches for data assimilation. So we have a point here. The point is that you want to use this data assimilation, you want to improve the accuracy in your data using this data assimilation. But the problem is that data assimilation is a large size computational problem, and you want to solve that in real time. The point is that that function that you want to minimize doesn't really matter if you try to do that with variational approach or with Kalman filter. You have different problems in terms of complexity and in terms of computational time, because with the variational approach you have to minimize a big cost function. With the Kalman filter you have to invert a big matrix. In any case, it can be it is computationally very expensive. So to face this kind of problem, obviously, you want to face this kind of problem, still keeping a good accuracy, so good efficiency, of course, but still keeping a good accuracy and also still trying to face the problem of big data. So just to recap, then you want to use data assimilation, so information from observation to improve your model state. But this is computationally expensive. Then you want to do something to improve the efficiency, so to speed up the process. But you still want to keep a good accuracy, and you want to be able to solve that in real world application, which means also facing big data problems. So to do that, you have two main possibilities. So the one that I will show you today is the one introducing simplifications and machine learning. I will show you reduced order models, nested models, etc. The other opportunity is developing scalable algorithms, which is like something I worked a lot over the past years, and I invite you to approach also these this point of developing scalable algorithms using, for example, the mean decomposition and power high performance computing. But for today, let's focus on the simplification side, the machine learning side. So machine learning for data assimilation, or better, we can be more precise. In this slide, I will talk to you about the artificial neural network at the service of data assimilation. What can do an artificial neural network for data assimilation? So Data assimilation, obviously, as I said, is a computational, very expensive problem. The main problem that, let's say, the state of the art of the hot topics with data assimilation for improving efficiency, accuracy, and there are a lot of groups worldwide working on this kind of, trying to solve this kind of problems is, one of the main problems is the non-linearities. So there are a lot of non-linearities in the data assimilation function. For example, that H operator, the observation operator, in some cases, for example, when you use data from satellites or some other kind of data, the operator is a transformation operator, is highly nonlinear, but to solve the problem of data assimilation, we have to linearize most of the time the observation operator. So the problem is, the point is, can we replace that, for example, with an artificial neural network, or the entire data assimilation process with an artificial neural network? And I will show you how recurrent neural network, for example, can help on this side. Then there is the other problem of these heavy background error covariance matrices. I'm sure over the past days you have seen what is the background error covariance matrix, the B matrix, that can be really huge, and usually in operational centers, but in any kind of real world application of data assimilation, these background error covariance matrices are simplified, are reduced, are so we have to work a lot on the simplification and the improvement of these metrics that otherwise are too big and too noisy and ill-conditioned. So I will show you how artificial neural network, for example, encoder decoder networks can help to do that, to treat these metrics. And finally, also the point that especially in the 4D data assimilation models, we also involve the forecasting model. And this can be very expensive, because imagine that if you want to include in your data assimilation a big system like the one for weather forecasting at each time step, it's computationally too expensive. So sometimes people just use a toy version or simplified version of the real system. So let's see if we can use, for example, surrogate models built with artificial neural network to replace the computational fluidodynamic software. And I will show you that this can be done, for example, with generative adversarial networks. So another question could be, okay, we have seen that artificial neural network can be used in support of data assimilation, but what about the other way around? Can the data assimilation be used for to support, to help, to improve machine learning models? The answer is yes, definitely, and we do that. The main problems with machine learning is that when you try to build a completely data-driven model, then you have a lot of problems depending on the dimensionality constraints. So when matrices are too big, noisy data, because when you build your model completely on data, it means that you also learn the error, the noise in the data. And sometimes also we have low quality data. So we can use data assimilation to merge together different sources of information and have a better quality data. In any case, even with machine learning, we always say that data assimilation is the missing piece. So data assimilation can really be used to support the machine learning community, to help the machine learning community building more robust machine learning models. So as you have seen in the first slides, the number of applications can be very general. In the next slide, let's focus only on one application, which will make easier the comparison among the models. So the application will be air pollution in big cities. So the computational fluidodynamic software is based on Navier-Stokes equation. And we are showing over the next slides a real test case scenario. Actually, this is the campus of Imperial College. On the top of the image, you see Hyde Park in London. So this is in South Kensington, which is a borough of the City of London. And on the right-hand side, you see the computational fluidodynamic version. So with these red points are the point where the busy junction, where there are busy junctions, so higher concentration of pollution. So as we have seen, data assimilation essentially can be in a very general formulation, considered as the solution of this problem, the admin of this function. So people working on data assimilation and machine learning essentially try to introduce machine learning in two main points in the algorithm. So one is replacing the forecasting model half. So this improves a lot the efficiency, so the speed up, because imagine that you have to update your state here, and you have a forecasting model that can be like thousands times faster than your computational fluidodynamic system. And then when you compute your covariance matrix, what we can do to improve the accuracy in how we build the covariance matrix. So the standard approach, the most standard approach, let's say, this is a software we have in the Data Science Institute we use to assimilate data for air pollution. Actually, what we implement, and something which is implemented in most of the common 3D variational data assimilation software. So we have simplification of the covariance matrix B. So using the singular value decomposition. So we have that essentially we decompose B with the singular value decomposition. Then we implement a transformation of the state. I'm not giving you all the details of the steps, but you can find all the details in these papers. So we implement a transformation of the state. So essentially we solve the problem in this new state. J is not J of U anymore, but it's J of W, where W is called control variable and is defined in a control space, which is several times smaller than the normal space. This is because we implement a truncation of the singular value decomposition. So with this, it works, we have good results. The only problem with that is that when you implement the singular value decomposition and then the truncation, you cut a lot of noise, but also you cut a lot of information. This is the reason why we were wondering, what if we replace this approach with artificial neural network approach? So instead of, So instead of just using that truncation, we implement an encoder-decoder approach. What does it mean? It means that you have your control space, you reduce the space with an encoder, then you have your observations, also the observation operator is an artificial neural network. You put together, so you use this new reduced space to train, to run your data simulation, and then to go back, you can use the decoder. So in case you are not familiar with what is an encoder or a decoder, so an encoder is an artificial neural network that can be used to reduce the features. So you have a bigger space and you compress the data in a smaller space. The powerful point of this is that you maintain nonlinearities. So with the truncation of the singular value decomposition, you cannot keep the nonlinearities. With the encoder and decoder approaches, you still keep the nonlinearities. So we have tried a lot of different, there are a lot of different implementation for encoder decoder technologies. We have seen that one of the best is this called a 2 codec. You can find all the equations, all the details, and also all the experiments in this paper. But what is interesting for us is the comparison with this truncational singular value decomposition, which is also implemented in something called principal component analysis. So PCA here stands for principal component analysis. So as you can see, the mean square error is reduced using, as expected, using artificial neural network. And this is because the obviously we are keeping the non-linearities, so you can improve the accuracy. And also in terms of speed up, we have like good results. And these are like a few comparisons. I can provide you these slides after the talk. So this approach actually is like so in the previous approach you reduce the space, but it's like the time is fixed in time. We were talking about a 3D approach. So the question could be, what if I want to also consider the time in all this process? Can I implement something which is in this reduced space that for expert of machine learning is called latent space? So can I consider an implementation of the data assimilation in the latent space, in the reduced space, also considering the evolution, the time of evolution? The answer is yes, and we have done that. So we implemented a Kalman filter in the latent space of the encoder, which is a reduced space. So to do that, we used a recurrent neural network, or better, we use something called long short-term memory, which is a recurrent neural network. These are the equations. So in this equation, x is the state variable, h is the transformed variable. So essentially is you solve your system, your variable in the small state, in the small space is this h. And here is the prediction correction cycle. I'm not sure you have seen in the previous days what is the Kalman filter, the prediction correction. I'm quite confident that you have seen that. So you have this prediction step, which is the step with which you go forward in time, and then you correct the step using information from the observation using the correction step. So the equation, the Kalman filter equation in this reduced space can be translated in this way. So instead of having the standard x and the standard y for the observations, here you have h, which is your variable in the reduced space. So let's see an application of this. Let's see how it works. And this is an application, still, as I said at the beginning, air pollution. This is for an indoor placement. So this is what happened. This is the test case. This is a room in this building. This is in south of London. It's a real building. So there is a window here and two windows here. So when you open this window, you see that the fresh air, let's say, starts to come in. And then after a few time steps, you can see how the air in the room can change completely. So we try to assimilate data from sensors in this room, in this computational fluidodynamic simulation. And we did this, we compared the results that we obtained doing this in the reduced space or doing that in the physical space, in the real space. So when you do that in the physical space, which is on the bottom, so you can see that in terms of execution time, you are gaining, let's say, 3 orders of magnitude, so which means the speed up of 1000. And also in terms of accuracy, especially if you consider an arc matrix which is small, which means you are giving a big, let's say, bigger importance to the observation. So usually the values of R are small when you trust more the observation, let's say. And in that case, you have an improvement, a strong improvement also in terms of the mean square error of up to 3 orders of magnitude. So why this? This happens for several reasons. Of course, the reduction in terms of execution times happens because you are solving the problem in a reduced space. But also the mean square error, the improvement in terms of mean square error is because when you do that, when you compress the data, you are also a bit reducing what I was introducing at the beginning, the condition number that is a parameter that propagates the error. So you can find, as always, more details in the paper I'm providing on in this slide. So all that, the previous question, we're just trying to help the existing data assimilation, to support the existing data assimilation, both to improve the accuracy or to improve the efficiency, speed up the process, etc. But another interesting question that I will ask you, and I asked it to myself at the beginning, was, but what if we want to use machine learning in that time steps when we don't have observations? So let me be more clear. So what if we, for example, especially in some kind of applications, and air pollution is one of these applications, we cannot have sensors there, for example, in a room all the time, or in the city, distributed in the city all the time. So we have stationary sensors, but also we have some sensors that are just, you know, they can stay there just, for example, 1 month and then done. What can we do to learn something from this information and then use this process also in the future when we don't have observations? And this is how we try to do that. But before going forward, I see there are a few questions, or I can start to answer all the questions at the end. I'm not sure.
As you like. Yeah, you can have a little break and look at the questions that are now. Yeah.
Yeah, because otherwise it will be like probably.
So we have 2 questions on the HackMD. I can read them for you if you want. Do you have any idea what types of physical processes are better handled by machine learning than data assimilation, like based on their degree of non-linearity?
Oh, yeah, but actually there is a theorem that proves that any nonlinear system can be learned by artificial neural networks. So I would say that when you have highly nonlinear problems, artificial neural network is definitely, let's say, more power. And then
Second one is from me, actually. So
okay.
You mentioned earlier that the encoder is able to preserve nonlinear relationships. And I know that, for example, principal component analysis are very good at maintaining linear relationships because they are linear operators. And at the same time, when I want to design transformations that can preserve nonlinear relationships, then they mess up the linear relationships. So I often have to choose between some relationships. So I would like you to develop a bit the idea. How is it that can we preserve a subset of nonlinear relationships? What's your approach on that?
So it's like, as I always say, it always depends on the problem. So obviously you have to consider that even implementing an autoencoder is it depends on a lot of hyperparameters. So you can definitely set up the hyperparameters in a way that you can preserve depending on what you want to preserve, some characteristics of your data or some others. So it's not just, you know, it's like saying also for data assimilation, no? Depending on what you want to reach, then you set up the parameters in a way or in another. So without encoders, you can keep non-linearities, yes, of course. But then there is, depends on some hyperparameters. So if you set up the hyperparameters in a way that are more strict, then all the non-linearity will be kept. But then if you know that there are no non-linearities that you want to consider, so there are not so strong non-linearities, you can set up the hyperparameters in a way that they are not, like, let's say, the back propagation that you implement is not so strict in maintaining that kind of information. So it always depends on how you implement that.
Yeah, it's supervised somehow, yeah.
Yeah.
Okay, thank you.
Okay, so I will go a bit forward with the slides. So as I was saying, can we try to use data assimilation, so machine learning, to learn the data assimilation approach? So the idea we implemented is very easy. So we have our computational fluidodynamic running, then we do data assimilation. We have our observation, we do the data assimilation. And then we compute this misfit between the computational fluidodynamic and the data assimilation. Why? Why we are interested in this misfit and not the misfit between the computational fluidodynamic and the observations? We are more interested in this misfit between the computational fluidodynamic and the data assimilation because we are assuming that the data assimilation is our ground truth for several reasons. In some application, unfortunately, the observations are very noisy. So we don't want to trust completely the observation. We don't assume that the observations are our ground truth. So we assume that the data assimilation of the computational fluidodynamic and the observation is the ground truth. So we have these misfit, and then we compute the misfit for several time steps. After that, we have the collection of all these misfits, and we train an artificial neural network. So the artificial neural network then will learn this misfit. What's the difference between the standard data assimilation and this kind of data assimilation that we call deep data assimilation? So the standard data assimilation, you run the data assimilation, then you run your CFD, then you run again your data assimilation, a sort of not really restarting the new process because you have information from the previous time steps from, for example, in a Kalman filter from the backward error, covariance matrices, which are updated. However, is like almost restarting a new process. With this deep data assimilation, you take into account all the past in your process. So, and let's see how this can be implemented. So this can be implemented in this way. So what we have done, we have implemented the standard data assimilation. So you have your computational fluidodynamic model, you have your observation, you do your data assimilation, then you have your data. We did it in a reduced space, so we use PCA, but as I said before, it depends if you want to use PCA or autoencoders. In this case, this block PCA can be replaced with an autoencoder. In this case, we didn't need to maintain the nonlinearities, so we use the PCA. And we have in our, then we compute the PCA, we reduce the space of this data. We do the same for the model data. So actually we compute the misfit, this misfit in the reduced space. Then we train this machine learning model. So we build this function and then we just couple this machine learning function with the computational fluidodynamic model. So what does it mean? It means that you have your computational fluidodynamic model, you don't have to touch it. And this is useful, especially for operational centers, because it's very difficult trying to modify part of an operational software because they are very stable, etc. So it's like it can be difficult. So in this way, you keep your computational fluid dynamic software, you don't change it, you just train this neural network, and then you couple the neural network with your forecasting model. And these are few results. So let's see what it means. So in terms of execution time, this deep data simulation is completely machine learning based, so it's 1,000 times faster than a standard data simulation. But what is more interesting is checking the in terms of accuracy. So in terms of accuracy, we have that data simulation in deep data simulation provides almost the same results. This is in the training part. In the forecasting, same. So deep data simulation and data simulation are both more accurate than just the model data, and more accurate than a standard data simulation. So the red line is a standard data simulation, the blue line is deep data simulation, the green line is the standard data simulation in the reduced space. So another example, I'm giving you an overview of a lot of different approach that you can use to implement machine learning with data simulation. Hopefully it can be like an inspiration for your future works. So to go forward, at the beginning I said another way to use machine learning in support of data simulation is replacing the CFD model completely. So build surrogate models which are completely data driven and that can be very, very fast with respect to a CFD. So, and this is what we implemented here. So these are, I will go fast on this because this presentation was mostly on the data simulation side, but I wanted to tell you a bit about the possibilities to implement surrogate models, so that some models can completely represent the dynamic behind a computational fluid dynamic. And this is done essentially always with the same technologies. It's like there are a bunch of basic technologies like encoder, decoder, recurrent neural network. Again, here there is this LSTM, long short-term memory, which is a recurrent neural network. And again, we combine them to have like these models that is order of 10 to 4 times faster than a standard CFD simulation. I will briefly tell you another way to do that, which is using generative adversarial networks, just in case you will see in the future, or if you are already familiar with generative adversarial network. They have been used a lot with image processing, especially facial recognition. But we are also using that for fluidodynamic now. And I think there are people worldwide, also people from DeepMind and other companies, big companies worldwide, which are implementing this kind of technologies. The reason is always the same, trying to build a surrogate model of the fluidodynamic models that can be faster. And also in this case, we have that this surrogate model is definitely faster. So we have like, instead of 172 seconds for time step, we have only 1.1 second. And we have 0.25 seconds on a GPU. So it's like, is really fast. 0.25 seconds is real time, so it's very fast. However, sometimes the accuracy can be, we can lose the accuracy. So what we have done is we have used the data simulation also to improve the accuracy. And as you can see on the top right, there is like this is the result of this latent generative adversarial network with data assimilation. So also still to be just inspiration, so just to give you an inspiration more than too many details on these slides. This is how you can use artificial neural networks, so these surrogate models, to predict something that was not simulated by your CFD before. I'm telling this because over the past years, a lot of work have been done to build surrogate models, fast models. However, the point is that when you build surrogate models that can copy the CFD, means that if you don't have that simulation from the CFD, then you cannot replace the so you cannot simulate something different. This is not true anymore. So we are using artificial neural network to simulate something which has been not simulated by the CFD previously. So this is just an example of air pollution at a bus stop. So the bus is arriving, is stopping, is starting again, and then this is how the deposition of the pollution on the floor happens. So the CFD that we have is just for one bus. But the question was, what can we do? Can we try to predict the same for two buses crossing? And this is what we tried to do, completely data-driven, same technologies. As I was saying before, it's just a matter of setting up the proper hyperparameters and combining the technologies in the proper way. So in this case, we have still autoencoders, recurrent neural network, data assimilation all together. And another point is that this can be very, very fast. So it's 1.2 seconds, which is very fast. So this is almost to close this presentation. Usually, all these models that we have seen, the combination of these models, have been implemented in the algorithm level of the math stack. If you consider the math stack from the real world physical model, mathematical model, approximation through all the steps in the system, all these models that we have seen have been combined in the level of the algorithm, say. So, and I grew up with this sentence of this quote of Alan Perlis when I was a PhD student. It was like adapting all programs to fit new machines, because it was the era of the GPUs, etc. And the quote was like, adapting all programs to fit new machines usually means adapting new machines to behave like old ones. And it was really true. So we had to rearrange the mathematical models to be able to use the machines, the new GPUs, in a proper way. And I say the same for data scientists. So now we are literally in the era of the data. If we adapt all these algorithms to the new data, we are not using the power of the new data. For example, still talking about nonlinearities, if we don't just try to ask to the data if there are nonlinearities, instead of just assuming that there are or not nonlinearities, we are not using the power of the data that we have now available. So instead of making an assumption, now we should just ask to the data. This is the reason why the data assimilation that we are as group implementing over the past couple of years, let's say, is at the level of mathematical model. We call that neural assimilation. What is neural assimilation? Easy idea. Neural assimilation is a neural network that emulates what a data assimilation, the whole process of data assimilation, does. So the idea is not difficult, it's easy. So you have your forecasting data, your observed data, you have this recurrent neural network, which is like two recurrent neural networks coupled. in a way that there is an information that passes from some layers to the other layers. So this is completely a new neural network, but this is just replacing the data assimilation. We have proved that. You can find the details in the paper. To implement that, we used LSTM. So probably you were asking why LSTM all the time. So since the beginning, LSTM, long short-term memory network, is very powerful because it is very accurate when you try to learn the time series. So as we work a lot with time series, for us, LSTM is like one of the best models. And also because they are very easy to be coupled. So this is the reason why we use that. So this is an experiment. This is the first experiment in 1D, how to use a neural assimilation to emulate a standard Kalman filter. And this is what happened. So this is like the oxygen passing through the blood-brain barrier. So this is the result of Kalman filter, and this is the result of the data assimilation. So as you can see, we have like same accuracy. And you can see also here exactly the same accuracy. In terms of execution time, let's say almost, because the Kalman filter takes 158 seconds for running. The neural assimilation in the training takes time. So it takes 121 seconds. In the prediction side, so when you have finished the training, then it's just 0.1 seconds. I wrote down this question here because it is a very popular question, and in case you are not thinking about that now, it could be useful anyway to know how to deal with this problem. So the question was, what if I want to add new time steps? So because with the artificial neural network, with machine learning, a lot of people say, okay, I trained this network, and then if I want to add more information, there is something called fine tuning. So if you implement your network in a way that then you can just adjust the network, then it's not a problem. You don't have to retrain the network from scratch. You can just adjust the network, adding new time steps. And we implemented the same just to show you that the blood-brain barrier was a 1D almost problem. We have done the same with air pollution, having the same results. So the optimal interpolation takes 276 seconds. So the neural assimilation just few seconds in the prediction side. So I want to just close this presentation, saying that there are other approaches, other ways to use machine learning to help and support data assimilation. And this is, for example, capturing the best data in a data set, or, for example, using machine learning to select optimal locations where you can put sensors, or when you have data from satellites, instead of optimal location, it can be optimal positions. So which data from satellites, which location you want to assimilate from the satellite. Yeah, to do that, you can use Gaussian processes. I will not give you details about that. But if you are interested, you can always send me an email. I can send you more details. For all these models that I was showing, we have the code available. So in case, and we are happy to share. So we have our GitHub, but in case you want to get access, just please send me an email. We are happy to share all our codes and happy to disseminate everything. So feel free to ask. And I want to leave you with this quote of Albert Einstein saying, "The true sign of intelligence is not knowledge, but imagination." And I always say that the imagination is the key, and the inspiration for you should be this one: imagine and then do that. this is one post, and I wrote for a blog of at Reading University, which was saying, imagine a world where it is possible to accurately predict the weather, climate, storms, tsunami, and other computational intensive problem in real time from your laptop or even mobile phone, etc., etc., etc. And it was 2018, and it was like at the beginning, I was just trying to do that. And now we are really going, not me, worldwide, group, a lot of groups worldwide, we are really moving towards this possibility. So as you know, a teacher to students, imagine and try. And thank you.
Thank you, Rossella. We have two more questions from the chat. So there's a third one being written now. So we start with the first one. It says, in your case, does PC achieve some kind of hidden localization? So did you compare with usual localization techniques? I'm not sure if localization is, say, something you have addressed today.
No, I haven't addressed that today, but yes, we also implement localization, but we have our own way to implement localization because we implement a lot of domain decomposition. So that can be called like a geographical localization. So trying to solve smaller problem with an overlap among subdomains in a way that you can pass the information from one subdomain to another, but keeping the problem local.
Okay, yeah, that was new to me. Then, well, I had a question. So you seem to find that yeah, everything can be solved. And my question is about how far can we really yeah, extrapolate these neural nets? And would you, yeah, if I gave you climate projections, say, it's coming from a neural network, would you trust it?
It depends on how they build this. And my answer is yes. And, because neural network can be, so one of the problems with neural network is that everybody tries now to use that. But if you are no expert of the mathematical model behind, as for everything, no, even for data assimilation, a lot of people can use data assimilation and then they even increase the error in the data instead of reducing the error because they don't know about the daily conditioning, they don't know a lot of stuff, no? So they use that in the bad way. But if you are expert of that and you know how to control that, it's a mathematical model, a neural network model. It's not like something completely far from our knowledge.
Yeah. I can be a bit more precise. You had the examples of the two buses that cross each other in a canyon. Yeah. So when two buses cross each other, they generate a lot of turbulence, small-scale turbulence between them. In the plains of the Middle East in the US, they can start a tornado. But yeah, I haven't seen that. I've heard about that.
Yeah. But Lawrence, Lawrence everywhere.
Yeah. So. What features did the neural net recreate that were not in a CFD? Did you find these sort of eddies and turbulence?
Yeah. So now there is something, I don't know if you are if you have already seen that, but there is something called physics-informed neural network. So what is that? Yeah, so this is the future. I'm telling this now today, and you will see. I'm quite sure about that because this is exactly what we were expecting. So the physics-informed machine learning is machine learning that in the training process include the CFD, the dynamic system. So it's literally learning the dynamic system from the CFD in the training process, not from the data of the CFD, from the CFD. So it includes the CFD. So then what happens? When you try to simulate something, then you have, is like you have the information of your dynamic, your CFD in the neural network.
Mm-hmm.
It's computationally very heavy, extremely expensive, because imagine that you have to, it's like when you do like a 4D bar and then you have to involve the forecasting model. Mm-hmm. It's something like that. So in your iterations, you have in the training part, you have the CFD that has to run, that has to run, that has to run. But at the end of that, after you have finished, you have this neural network, which is really fast, as a neural network can be, as in our brain, fortunately, but is also very accurate because it has the CFD in the training process.
Okay. Right.
So, yeah, but it's let's say the state of the art.
Yeah. Okay. But I will be happy to see that. Yeah. Then there's more questions on the chat, so I should not spend too much time on this one. So how do the combinations of data assimilation and neural network impact hyperparameters, like the number of layers in, for example, deep learning applications?
So we have seen that data assimilation for machine learning, this is right. So in this case, it impacts the hyperparameters because the backpropagation is faster. So the weights are like the convergence of the function is very fast, and so the weights are completely customized on the observations.
Okay, that's an efficiency. How can we account for the errors made by the neural network in the data assimilation? Is it a type of model error?
So how we can compute the error for the neural network and for the data assimilation?
I guess account for the error is having an assumption of what are the model errors of the neural net.
Same. Usually we use the mean square error. Just a few times we use the absolute error, but usually we use the mean square error.
Okay. Then last one from Michael Ying. Say we have a really erroneous model. Can machine learning help detecting what component in the model is wrong given the data?
Interesting. Yes, but this is with parameters estimation.
It can identify which parameter is more source of errors.
Yes. I see Rossella, is the code available somewhere? Yes. We have our GitHub. If I can stop sharing, I will send you
the link. Yeah.
Exactly. I will post the link. So is this one.
Okay, so from the other projects. Yeah.
This is the link.
Okay. Yeah, we'll copy that to the Markdown document. So, are there any more questions for Rossella? We still have time actually because you completed very early, 10 minutes beforehand. So all of you, if you have questions, please don't hesitate.
Yeah.
I don't see raised hands or.
Okay, they can always send me an email.
Yeah. And I'd like to thank you a lot for this very enthusiastic presentation. Maybe now it's since we are a bit early and we have a bit of time before the coffee break, we can just turn on your cameras. Those of you who want to turn on your cameras and try to take a group picture. Would that be nice? Please.
Yeah, that would be good.
Go ahead.
At that time, I was listening to this event organized by NFL on synergy grants.
Don't be shy. This will only be posted on the Lancer Center webpage. There's nothing to fear. I don't know if we can fit more pictures in the.
I think you have to do 2 pages.
2 pages.
Yeah.
I see.
Success.
View.
Okay. What did I mention?
I don't know how to do 2 pages. Can someone who's good at Zoom make 2 pages and take a screenshot?
No, it's like taking 2 screenshots.
Yeah,
Yeah.
screenshot of each page.
Ah, yes, correct. Yeah. So now I'll go to page number 2, and there's much fewer people on page number 2. I'm sorry for that. Those ones. They'll be much more in the focus. I see more people switching on their cameras. That's nice.
We would get 80 million for 10 years, 80 million euros for 10 years, and this is 10 million for 6 years. So it's not that.
Sure, you just escaped from your camera. That's not nice. Turn on the camera and then run away.
And because it's ERC, you don't need to involve other countries or even other. Yeah, you can have a
review.
So
now it's time. Please smile and I'll take a picture. Thank you, everybody.
The crucial aspect, and that's where I think we're struggling.
So, in the meantime, maybe some of you have had more questions for Rossella.
Side by side, it's 2 groups who, through discussing, are creating new.
So, what I can see at least.
So maybe
now we, yeah. Yes, please.
I was wondering because some people have the tendency to create very deep models in order to, you know, like in deep learning, in order to try to account for everything, because they think that maybe more layers means it's more accurate. But that's a problem because you are like not considering like that you may be overfitting or having more complex stuff. What will be your advice to assess like that the layers are actually having the level of complexity of your model, or can you give some advices about that?
Yes, of course. So there are some ways to avoid overfitting. One of the way is actually the last slides I was showing about optimal placement or optimal selection. It can be also that algorithms are based on the maximization of the mutual information, the maximization of the entropy and the mutual information. So there are algorithms that are able to give you from a big data set just the data which are more meaningful, let's say. Then you can use that one. It's even better because you reduce a lot of noise and you avoid some problems with overfitting, etc. It's a way to balance the data that I think it can be very good.
And there's another question from the chat, actually. The question, I don't understand the difference between surrogates or physical model and the NN learning from the CFDs. Both learn from the equations, right? Don't they?
No, it's just a name. Surrogate models means a model which is built on from the data using neural network or other kind of data-driven model. It is just a name.
I have a question. Thank you for the presentation. It's not really a question. It's more an affirmation to see if I understood well. In all the experiments you've presented, you have access to some ground truth from, for example, CFD simulation, or to train the autoencoder or the PCA. You have access to some ground truth, but have you ever tried to train a whole system only using incomplete data from observation?
Yes, because we don't have always, not in all the applications we have the CFD. For example, we have worked on cryptocurrency market. We didn't have any CFD behind that, which is something completely different from geoscience. Or for example, Twitter data. We have used data assimilation and machine learning for the Brexit. let's say, to predict the Brexit, let's say. And we use it, yeah, you all also, it's still our data, no? We try, it's fun. And and we didn't have any CFD for that, obviously, because there is, unfortunately or fortunately, we don't know, the human sentiment is not predictable yet. So yeah, it can be used for.
Thank you very much.
All right, then. So if there is no more questions, I think we can move on to a well-deserved coffee break. And I see Alberto is not here yet, so I will just reconvene at 11, everybody, so that we don't give a surprise to Alberto when he comes. So please stay online and enjoy your coffee. See you soon.